This lab uses the momentum principle, or Newton's second law, to determine information about the interactions of a system and its surroundings from the knowledge of the system's motion. Using data from a CSV file and the position of a black hole affecting the star, as well as the mass of the star, I was able to determine the mass of the black hole by constructing a computer model. The mass of the black hole was shown to be 3.98 times 10 to the 31st power kilograms. The momentum principle states that the net force on a system is equal to the change in momentum of a system divided by time. This lab will be using position to find velocity, velocity to find momentum, and then the change in momentum over the change in time given as dp dt. The parallel component of momentum is found by using the derivative of the magnitude of the momentum with respect to time multiplied by the direction of momentum, denoted as p hat. F net is set equal to dp dt, and their respective perpendicular and parallel components are equal. It is important to note that though F net is equal to dp dt, and their respective components are equal, they are not the same thing. dp dt is simply describing the motion, while with the parallel component describing change along the axis of p, so the speeding up and slowing down. The perpendicular component is denoting the change along the axis perpendicular to the momentum, so the change in direction. F net is affecting the motion. It is more accurate to say that dp dt is a result of F net. The components of the net force are causing the components of dp dt. Provided was the mass of the star, our system, the time step, the position of the black hole, and the positions of the star in a CSV file titled Star Data. Why do we need the mass of the star and the black hole position? To answer this, it must be stated that this lab is assuming that the force of gravity between the black hole and the star is the only force on the system, such that F net equals Fg. The magnitude of Fg equals the universal gravitational constant, g, times the mass of object 1 and object 2, divided by the distance between objects 1 and 2. By using the code to solve for F net, we can set F net equal to this equation, enter in our initializations, and solve for the mass of the black hole. So let's do that. First, the data had to be extracted from the CSV file. Then the velocity at every position was solved for. Then the momentum principle was applied to velocity. Here we can see the equations entered into the code. Finally, the equation for gravity was coded in. With our initializations defined before the while loop, the code then printed out the time, F net, and its parallel and perpendicular components, as well as the mass of the black hole. As stated earlier, the mass was found to be 3.98 times 10 to the 31st power kilograms. What if? What if the mass of the black hole was changed, but the path wasn't? Would we be able to calculate the new mass? In short, no. The path is how we determine the force on the system. So if it is unchanged, then we would continue to get the same F net, and conclude that the mass is also unchanged. However, in order for the path of the system to remain the same, the F net can't change. That means that when the black hole gets swapped, another force also begins to interact with the star. We would have to know more about the system's interactions to determine what the secondary force is. But if we determine one force, we might be able to determine the other force, though this is just assumption. Without a secondary force also being introduced onto the object, then the path would not remain the same, and we would be able to compute the new mass. Note, the diagrams are assuming an increased mass, and they are not to scale. In conclusion, for this example, the mass of the black hole was found to be 3.98 times 10 to the 31st power kilograms. It was only able to be calculated because the force of gravity was assumed to be the only force on the star. The analyzation of the path of the object only yields the net force. To determine specific forces, assumptions must be made about the system's interactions with its surroundings.